Gentlemen, observe the profound connection between the magnetic and the electric forces which govern our world.
Today, we are peering back into the shadows of the early 19th century to understand how humanity began to grasp a pair of fundamental forces that have governed the universe for billions of years: electricity and magnetism.
These invisible forces are everywhere, yet for the vast majority of human history, they were just mysteries. Sometimes terrifying, sometimes useful, but never really understood.
Well, we know some early cultures, particularly the classical Chinese, they understood the Earth's magnetic field enough for navigation, thousands of years ago.
Right, but the mechanism, the why of it all, that remained a complete enigma.
It's because electric effects are so ephemeral in nature. Positive and negative charges, they just want to find equilibrium instantly. So you get lightning, you get static electricity, but a continuous controllable force. That was hidden. It was tucked away in the very structure of matter and space.
And then along came our subject today, Michael Faraday, born in 1791. And get this, a full century before scientists even had a concept of the electron as a particle.
And he brought about such a radical, almost philosophical change in how we understood these invisible fields that it fundamentally redefined civilization.
It's a huge shift, isn't it? Moving from seeing these things as like parlor tricks.
Right, or curiosities. He moved us to understanding them as unified foundational parts of reality itself. His work established that inseparable link between electricity and magnetism, electromagnetism. I mean, that concept powers everything you and I are touching right now.
But here's the paradox, and this is what makes his story, for me, one of the most compelling in the history of science. Faraday, this English genius of experimental physics, he achieved all of this without ever going to university. No formal academic education. And crucially, he lacked any real mathematical skill. He never mastered calculus.
So how did he communicate these revolutionary ideas? Not with equations. That's what baffled everyone. He used meticulous descriptions, incredibly detailed drawings, and schemes. He was an outsider in a world dominated by the mathematically trained Newtonian elite.
So our mission today is to unpack how this incredibly humble man, driven by experiment and faith, not formulas, was able to see what the entire scientific establishment could not.
We're going to trace his path from utter poverty to scientific leadership and really understand how he moved humanity, practically and conceptually, from the age of candlelight to the electric age.
The age of candlelight. To really get the scale of his achievement, we have to paint that picture. Just how dark was the pre-Faraday world.
It's actually hard for us to visualize. I mean, a large city like London was truly defined by darkness.
Yeah.
A middle-class family, being careful with money, might budget for only one single candle per night.
One candle. What does that even mean in terms of light?
Well, if you translate it into modern terms, the total illumination for that whole family for an entire evening was about 1/100th of the light you'd get from a standard 100-watt light bulb.
That's basically living in deep shadow. You couldn't read, you couldn't work, your life just stopped when the sun went down.
Precisely. And the alternatives, they were barely better. The wealthy, they had gas lamps.
Which sound better, but they had their own problems.
Well, absolutely. They were expensive, they were greasy, they were prone to leaking, and they poisoned the air indoors. People got headaches, felt noxious. And outside, the street lighting was a joke.
So what was that like? Walking down a London street in, say, 1850?
Even by then, the gas lanterns were maybe equivalent to a modern 2.5-watt bulb, and those were spaced 30 meters apart.
So you're walking from one tiny pool of light through absolute blackness to the next tiny pool of light.
It was genuinely terrifying. People would hire torchbearers just to get home safely. So yes, the age of darkness, it really underscores the profound practical importance of everything Faraday was about to do.
And his unique perspective, as you said, fueled by faith and experiment.
Yeah.
That was the spark that was going to light up the world.
That was the spark. Absolutely.
Okay, let's unpack how a mind like that emerges from such humble beginnings. This is section 1, The Boy and the Bookbinder. Michael Faraday, born 1791, Newington Butts, just outside London, son of a blacksmith.
And his early life was one of extreme poverty. His father, James, was diligent, but he was often sick, so he couldn't work steadily. The family was so poor that the sources actually state they had to seek public assistance in 1801.
And that experience, that sense of want, it really shaped him, but it also reinforced the values his family taught him through their religion.
That religious background is, I think, foundational to understanding his entire scientific approach. They were members of the Sandemanian community.
Which is a very strict Protestant sect, right?
Very strict. They focused on an extreme literal adherence to the New Testament. community, spiritual integrity. And their creed had these instructions that would dictate how Faraday later dealt with fame and the establishment.
So what did they believe that was so different?
Well, they took Christ's teachings on wealth literally. They saw poverty as a virtue, the whole camel through the eye of a needle. And most importantly for his story, they required members to reject worldly honors, no high social positions, no titles.
So no knighthoods, no presidencies of scientific societies.
Exactly. And that will echo throughout his entire career.
Given that background, his lack of formal education is almost, well, tragically predictable. His schooling ended very abruptly.
It did, and the story around it is just incredibly revealing about the times. Michael had a lisp. He couldn't pronounce the letter R, so he'd call his older brother Robert Voveti.
And the teacher's solution was physical correction.
Right. He told Robert to go buy a cane so he could beat the lisp out of young Michael.
Which is just brutal.
Robert, who was already a blacksmith's apprentice, was just outraged. He threw the money down, told his mother, and that was it. That was the end of Michael Faraday's formal education.
So he's left without any typical path forward. No school, no university. In 1805, he gets apprenticed as a bookbinder to a man named George Rebow.
And that mundane job, that was his real university.
An intellectual osmosis. He's binding the books of the scientific elite.
And he's not just stitching the covers, he's devouring the pages. He later credited 2 books in particular, the entry on electricity in the Encyclopedia Britannica, and a book called Conversations on Chemistry by Jane Marcet.
That second one is fascinating because it was written by a woman for a lay audience. It shows he wasn't seeking out dense mathematical texts. He wanted clarity, a mechanical understanding of how things worked.
And he didn't just read. He immediately started doing, he set up his first totally primitive makeshift lab right there in the basement of the bookshop.
And the detail about his first piece of equipment really connects him back to his family.
It does. He was determined to build an electrostatic generator, a machine to make sparks. It needed an axle, and that axle was forged by his father, the blacksmith.
So you have this direct link between the old world of craft and the new world of science.
A beautiful link. The whole thing cost 4.5 shillings, which he had to borrow. And that crude device is still preserved in the Royal Institution today.
This intense self-education eventually leads to his big break in 1812. A customer, a member of the Royal Institution named Dans Jr., notices the detailed notes Faraday's bound into a book.
Right, he recognizes this raw talent and gives him 4 tickets to hear the most famous scientist in England, Sir Humphrey Davy.
And Davy at this point is a superstar.
He's the epitome of success. The Royal Institution was sort of the Olympus of science for the upper class, and Davy was its director. He'd also come from a poor background, but he had made it. He was knighted, married into wealth. He was the absolute authority.
So Faraday goes to the lectures, meticulously transcribes 96 pages of notes, binds them beautifully, and sends them to Davy asking for a job. Any job.
And Davy initially turns him down. Politely, but no. So Faraday has to go back to bookbinding, this time for a much harsher master who hated his scientific pursuits. It must have been crushing.
But then fate steps in.
In 1813, Davy's personal assistant gets filed for fighting. And Davy remembers the young man with the incredible notes. He offers Faraday a job as his laboratory assistant.
This is where Davy famously said, "Faraday is my greatest discovery."
He did. But Faraday's education was about to become a profound test of his character. He immediately goes on this European tour with Davy and his wife, Lady Jane Davy.
And on one hand, it's an incredible opportunity. He's meeting the great scientists of Europe, learning French and Italian. On the other hand, it's 2 years of just relentless humiliation.
Lady Davy in particular saw him as a servant. She constantly demeaned him for his low birth and lack of social polish. She'd make him eat with the valets and the maids.
That must have been incredibly painful.
It was, but it forged this iron resolve in him. He endured it because the educational opportunity was irreplaceable. It solidified his determination to become a great natural philosopher, completely independent of social rank.
So when he gets back to London in 1815, he's not just Davy's apprentice anymore. He's ready to challenge the very structure of the elite science that had scorned him. So Faraday returns, ready to make his own mark. This brings us to Section 2, turning electricity into motion. And the scientific world was absolutely buzzing about a recent discovery.
The stage was set in 1820 by the Danish physicist Hans Christian Ørsted. His discovery was actually quite simple. An electric current creates a magnetic field. He ran a current through a wire, and a nearby compass needle moved.
Which was revolutionary.
Yeah.
Until then, electricity and magnetism were seen as totally separate things.
Exactly. The prevailing view, because of Volta's battery, linked electricity mainly to chemistry. Ørsted showed it was also linked to force and motion.
But the great minds of the time, they were all trying to fit this new force into the old Newtonian box. Forces that act as straight lines, a push, a pull.
But Faraday, he noticed a crucial detail that the mathematically minded were overlooking. The compass needle didn't point toward or away from the wire, it deflected perpendicular to it. Sideways, and it kept moving in one consistent direction around the wire. This suggested a completely new geometry of force. It wasn't linear, it was circular.
And this is where his lack of formal math training was actually an advantage.
It was his superpower. He wasn't looking for an equation to describe two points interacting. He was looking at the shape of the action itself. He hypothesized that the wire was surrounded by an invisible, swirling vortex, what he would later call clotheslines of force.
So his thinking was, if the force is circular, I should be able to make something spin continuously.
Precisely. And to test this, he built the world's first primitive electric motor. This was September 3rd, 1821.
Break down the experiment for us. It sounds complex, but it was actually quite elegant.
Deceptively simple. He took a magnetized rod and stood it upright in a pool of mercury. The mercury acted as both a conductor and a low-friction liquid bearing. Then he dangled a current-carrying wire into the mercury near the magnet, and the magnet began to rotate continuously around the wire, driven by that invisible magnetic vortex.
He had converted electrical energy into continuous mechanical movement, into work.
The first time it had ever been done. The report he published made him an international star overnight, completely independent of Davy.
But that success came at a bitter personal cost: Davy's jealousy.
The mentor could not stand to be eclipsed by the protege, especially one from such a low social class. Davy immediately started spreading rumors that Faraday had stolen the idea from another scientist, William Hyde Wollaston.
And was there any truth to that?
Not really. Wollaston had mused about the idea and had tried some clumsy experiments, but he'd failed. Davy used this vague speculation to accuse Faraday of plagiarism.
So Faraday was forced to defend himself.
He was. He published a detailed account tracing every step of his independent work, which completely cleared his name. And to his credit, Wollaston himself came forward and defended Faraday's originality.
But the damage with Davy was done. The tension peaked in 1824 when Faraday was nominated for the Royal Society.
Davy, as the powerful director, actively campaigned against him. He brought up the old plagiarism charges, he pressured people.
And yet, Faraday was elected.
Almost unanimously. And here's the detail that really speaks volumes. There was only one single vote cast against him, and everyone agrees the vote belonged to Sir Humphrey Davy.
A profound betrayal. The atmosphere must have been suffocating.
It was. But the tension finally lifted when Davy died in 1829. And only then was Faraday truly free to pursue the great question that had been burning in his mind for years.
The great reversal. If electricity can create magnetism, can magnetism create electricity?
The one problem that had stumped them all.
So this search for the reversal magnetism creating electricity was the absolute holy grail of physics at the time. And it led Faraday to his greatest conceptual leap, one that completely broke from Newton.
And the story of this breakthrough starts, interestingly, not in a lab, but with a moment of spiritual contemplation.
Right, he's on a trip to Switzerland thinking about his Sandemanian faith.
And he's watching a rainbow appear and disappear over a waterfall. He realizes that the light, even when it's not visible in that empty space, it doesn't truly vanish. It's still there, potentially. This reinforced his deepest belief in the unity and interconnectedness of everything in creation.
And that philosophical belief put him on a direct collision course with the reigning scientific dogma.
It did. The Newtonian worldview was built on actio in distance action at a distance. It meant that two objects, say the Earth and the Sun, affect each other instantly across empty space.
So space itself is just a passive, empty void.
Exactly. In the Newtonian view, if the Sun just vanished, the Earth would instantly fly off into space. The space in between doesn't matter. Faraday found this scientifically and, frankly, theologically incomplete.
His faith told him that space couldn't be empty.
He realized the space between two objects wasn't a void. It was filled with a dynamic physical connection, an invisible web of magnetic and electric lines of force. This was the revolutionary concept of the field.
So he's challenging Newton, the giant of physics, without even being able to read his calculus.
And that was his advantage. It freed him. He could see the world visually, mechanically. He wasn't constrained by equations that only described action between points. He was imagining the dynamic reality in the space around them.
So with this new idea, the field, he goes back to the lab. This leads to the crucial experiment on August 29th, 1831, the birth of the transformer.
This is the experiment that changed everything. He took a soft iron ring, like a big donut, and he wrapped two separate insulated copper coils around opposite sides.
He connects the first coil to a battery and the second coil to a galvanometer, a current measuring device.
And the absolute key to his success was observing the transient effect, the flicker. When he connected the battery to the first coil, creating a magnetic field in the ring, the needle on the galvanometer on the second coil gave a little kick, a momentary surge of electricity, and then it went straight back to zero.
Why back to zero? The magnetic field was still there.
Because the field was now static. It wasn't changing. But then, and this is the crucial part, when he disconnected the battery, causing the field to collapse, the needle flickered again, but this time in the opposite direction.
So electricity was only generated when the magnetic field was changing. At the exact moment it was created or destroyed.
That's it. That's the insight that every other great mind had missed. They were looking for a steady current from a steady magnetic field. Faraday realized the effect was instantaneous and transient. A changing magnetic field creates an electric current.
In this systematic approach, it went beyond just physics. The next year, 1832, he turns to the nature of electricity itself.
Right. He needed to prove that all the different kinds of electricity, static from rubbing glass, galvanic from batteries, were all the same thing. And in doing so, he firmly linked electric charge to chemical reactions. This gave us the laws of electrolysis.
Which basically said that the amount of chemical change is directly proportional to the amount of electricity you pass through a solution.
Precisely. It was a quantitative link between chemistry and electricity, and it suggested that charge itself came in discrete packets, a huge leap toward the idea of the electron decades later.
And to describe all this, he had to invent a whole new language for the field.
He did. He worked with a philologist, William Whewell, and they came up with terms we still use every day. Ion, meaning traveler in Greek, cathode, anode, electrolyte.
So with the principle of induction established, the next logical step was to make it continuous, to make it useful.
Exactly. The transformer gave you a burst, but industry needed a steady supply. So on October 28, 1831, he created the first dynamo, the homopolar generator.
The first machine to turn continuous motion into continuous electricity.
And again, it was disarmingly simple. He just rotated a copper disc between the poles of a horseshoe magnet. As the disc spun, the copper continuously cut through the magnetic lines of force, generating a weak but constant direct current.
It's the ultimate reversal of Ørsted's discovery. Motion creating electricity.
And yet, here's the tragedy of his time. The academic community, they still resisted his ideas. They saw this poor bookbinder talking about lines of force and thought it was unscientific, almost mystical. Where were the equations?
That's where James Clerk Maxwell comes in 30 years later. He was the great translator.
He was. Maxwell took Faraday's poetic, word-based ideas about the field and translated them into the universal language of mathematics. Maxwell's equations unified electricity, magnetism, and light, proving that light itself was an electromagnetic wave.
So Faraday didn't just invent the generator, he invented the entire conceptual framework for modern physics, even if it took a mathematical genius to write it all down.
As Einstein himself said, the work of Faraday and Maxwell provided the basis for all of modern physics.
So the conceptual groundwork Faraday laid moved almost immediately into the practical world. This takes us to Section 4, the electric age, the moment his ideas started literally lighting up cities.
The evolution was incredibly fast. Just a year after Faraday built his little disc dynamo, a man named Hippolyte Pixii in Paris built the first industrial-scale dynamo in 1832.
He basically took Faraday's principle and just scaled it way up.
He did. He used a big, rotating, permanent magnet moving past stationary coils of wire, which gave a much more powerful output. But it had a slight problem.
It produced alternating current, AC.
Right, because the magnet poles were constantly reversing as they passed the coils. And for the early applications, like electrochemistry, they needed direct current, DC.
So how'd they solve that?
Pixii quickly added a crucial component, the commutator. You can think of it as a mechanical flipping switch on the rotating axle. As the current reversed in the coils, the commutator mechanically flipped the connections, so the current leaving the machine always flowed in one direction.
It converted the natural AC output into steady DC, and that really opened the floodgates for industrial power.
It did. Engineers realized they could use electric motors, the thing Faraday invented back in 1821, to turn the dynamos. Then they hooked them up to steam engines and waterfalls, and that led directly to the first central power stations.
And this shift from noisy, dirty steam engines to quiet, clean electric motors in the 1860s and 70s, that just completely redefined industry.
The socioeconomic impact was immense. Before this, you had to build your factory next to a coal mine or a river. Now you could transmit power over distances. Electricity production quickly became a key metric for a country's GDP, its prosperity.
But his more abstract idea, the field, the idea that the invisible space around the wire mattered, that was put to a huge test in the 1850s with the transatlantic telegraph cable.
Ah, the great cable crisis. This was a massive vindication for Faraday. The financier, Cyrus Westfield, was trying to lay this 4,000-kilometer cable, and he was completely ignoring the warnings of the physicist William Thomson, who we now know as Lord Kelvin.
And Thomson was a huge supporter of Faraday's field ideas.
He was. Thomson warned Field that the problem wasn't just the resistance of the copper wire. The problem was the interaction of the field with the surrounding medium. The insulation, the iron sheathing, the seawater itself.
So it's a perfect illustration of the field.
Yeah.
The invisible reality outside the wire mattered more than the wire itself.
Exactly. Thomson was basically saying, the space around the wire is active, it's not passive. But Field just tried to solve the problem with brute force. He blasted massive amounts of high voltage down the cable.
And the result was?
Total failure. The high voltage created such a powerful field that the energy just dissipated into the ocean. The heat melted the insulation, the signal slowed to a crawl. It was a disaster.
So Faraday's abstract concept was proven correct by a massive, expensive engineering failure.
It was a monumental, costly victory for field theory. Thomson's next successful design was based entirely on Faraday's physics, using better insulation and thicker conductors, not more voltage.
And Faraday seemed to know just how big the applications would be. We have those two classic anecdotes.
Right. The first is with Prime Minister William Gladstone, who visited the lab and asked, "But after all, what loose is it?"
And Faraday's legendary reply, "Why, sir, one day you will tax it."
Which proved to be completely true. The British government introduced the first tax on electricity production in 1880.
And the second one, with the woman who asked about his new discovery.
"Madam, what use is a newborn baby?" He knew he had started something that would grow and completely change the world.
We also have to touch on his huge impact on chemistry, which often gets overshadowed by the electricity work.
Absolutely. In 1823, he pioneered cryogenics by using cooling and pressure to liquefy gases like chlorine and sulfur dioxide for the first time. He reached temperatures below minus 100 degrees Fahrenheit.
And then there's the discovery of benzene in 1825.
A perfect example of his practical roots. He found it while working for his brother's gas company. They were making illumination gas from whale oil, and in the oily residue, he isolated this new colorless liquid.
Which we now know as benzene, one of the foundational building blocks of the entire modern chemical industry.
It's indispensable. It's the base for plastics, solvents, synthetic fibers like nylon, resins. The list is endless. It's just incredible that his work was so foundational in both the electric age and the age of organic chemistry.
So let's move into the final phase of his life, which was really driven by this unwavering, almost spiritual quest for the unity of all of nature's forces. This is section 5, the unseen connections.
The sources show this relentless pursuit really took a toll on him. He suffered from nervous breakdowns, significant memory loss in his later years, probably from a combination of overwork and chemical exposure in the lab.
And yet, he recovered and plunged right back in, determined to prove his field theory held true everywhere. This leads to one of his most visually dramatic experiments, the Faraday cage in 1835.
He needed to prove, without a doubt, that electric charge resides only on the outside of a conductor. So he built this giant wooden box, covered it in aluminum sheets, and had it moved into the lecture hall.
And then he did the ultimate demonstration of scientific courage.
He had his assistant charge the cage from the outside with a powerful generator until massive blue sparks were flying off of it. He was buzzing with electricity. And then he calmly walked inside.
And how did he prove it was safe? That the field was neutralized?
He took his most sensitive instruments, electroscopes, inside with him. And he showed the audience that despite the violent storm of electricity on the outside, inside the cage, there's absolutely zero charge.
This is the principle of electrostatic shielding.
That's right. The free electrons in the metal cage instantly rearrange themselves to create an internal field that perfectly cancels out the external one.
And this principle is just ubiquitous in modern life.
It's everywhere. It's why you lose your cell signal in an elevator. It's how an airplane protects you from a lightning strike.
Yeah.
It's the mesh screen in your microwave oven door, keeping the microwaves inside.
But his ultimate quest was still unification. He was convinced that light had to be connected to magnetism.
He tried for years and finally succeeded in 1845 with the discovery of the Faraday effect. And here's a wonderful irony. He did it using a special piece of heavy lead borosilicate glass.
And where did he get that glass?
It was a batch that Humphrey Davy had forced him to make years earlier as tedious busy work, probably just to keep him distracted from his own research.
So the very thing designed to hold him back became the key to his greatest unifying discovery.
Exactly. He passed a beam of polarized light through this piece of glass while a strong magnetic field was running parallel to it. And he saw that the plane of polarization of the light actually rotated.
Meaning the magnetic field was physically twisting the light.
It was. This was the first proof that light could be physically influenced by magnetism. It was the final piece of evidence Maxwell needed to mathematically prove that light was, in fact, an electromagnetic wave.
He had unified electricity, magnetism, and light.
But his curiosity just kept going. He started classifying all kinds of materials. He discovered diamagnetism.
Which is the idea that some materials are actually repelled by magnets.
Right. Yes. We all know about ferromagnetics, things like iron that are strongly attracted. But he found a whole new class of things like copper, water, even apples and people that are weakly repelled. He hypothesized that if you carefully suspended a person in a strong enough magnetic field, they would turn perpendicular to the lines of force.
That is just a remarkable thought. And this legacy is completed by his fierce moral integrity, sticking to those Sandemanian beliefs.
He consciously rejected the elite status his discoveries earned him. He turned down the presidency of the Royal Society in 1857.
Famously saying, "I must remain plain Michael Faraday to the end."
He also refused a knighthood, and perhaps most commendably, he refused the government's request to help develop chemical weapons for the Crimean War on profound moral grounds.
And he was also dedicated to sharing science with the public.
He was the ultimate popularizer. He started the famous Christmas lectures for youth at the Royal Institution in 1827. They're still running today, televised by the BBC. His final series, The Chemical History of a Candle, is still a classic.
Even in his final years, his mind was fixed on the ultimate prize, a unified field theory.
He tried, unsuccessfully, to find an experimental link between electromagnetism and gravity. He was convinced that all forces must come from a single fundamental origin.
And in a final gesture of humility, he requested a simple burial.
He refused to be buried near Newton in Westminster Abbey. He rests in a simple tomb in the Sandemanian section of Highgate Cemetery. A simple end for the man who lit up the world.
It is truly staggering when you just, list his achievements. The motor, the dynamo, the laws of electrochemistry, field theory, the link between light and magnetism, the Faraday cage, benzene.
All achieved by the son of a blacksmith who was thrown out of school for a lisp and who never mastered calculus.
His story is just this powerful proof that world-altering insights don't always come from institutional authority or abstract formulas. They come from meticulous observation, unwavering curiosity, and the courage to challenge the established masters.
That intellectual freedom was everything. He wasn't constrained by the mathematical dogmas of his time. And that freedom allowed him to see that tiny transient flicker of a galvanometer needle, a detail everyone else missed, which ultimately gave us the entire electric age.
It's astonishing that one small momentary fluctuation observed by a non-mathematician is the basis for the entire electrical grid that powers our world.
And this brings us back to his final great unsolved problem, the link between the electromagnetic field and gravity. Faraday proved that an unseen field connects and influences everything. Maxwell translated the electromagnetic part of that vision into math.
But the link to gravity remains the white whale of modern physics. Einstein chased it his whole life and couldn't find it.
So, here's the final provocative thought for you to consider. Faraday's unique perspective, unconstrained by conventional thinking, allowed him to physically perceive the existence of the electromagnetic field where others only saw empty space. What if we, today, are too mathematically constrained to see the gravitational field in a new, conceptual way? What if we're
Gentlemen,
missing the equivalent of
observe the
Faraday's
profound
flicker because we're
connection
only
between
looking
the
for a certain
magnetic
kind of
and the
equation?
electric forces
What
which
revolutionary
govern
yet
our world?
undiscovered principles might be waiting for us if we just dared to approach the universe with Faraday's blend of humility, tenacity, and poetic imagination? What greater secrets does the empty space around us still hold?
Join us and keep your curiosity well fed. Who knows? The next video might be exactly what you didn't know you needed.